Hello and welcome back. Alright, so in the last video we talked about inheritance and virtual methods. In this video we're going to go ahead and learn how to practically use those. And the way we're going to go about learning this is we're going to implement a new data structure called the stack. Now a stack is a stack of items. Basically think about how you stack or how you put books on a desk when there's multiple of them. When you put one down, you put another one on top of it, then you put another one on top of that. So it kind of looks like this. One book, the second book, third book, and so on. And so the interesting thing to note about the stack is that the first one that you put in is the last one that you take out. And the last one that you put on is the first one you take off. So this is called a first in, last out data structure. The linked list is kind of a random access. You could put it in basically anywhere you want to and remove anywhere you want to. Well, in a stack, we go by this semantic that we don't actually remove the items in the middle. Okay, so how do we work with these? Well, we could just use a linked list and always call the push back and always remove the last one. But we actually want to constrain our users and give them a little easier functions to work with, so they don't have to care about the implementation details so much. So the three functions that we use are push, which pushes an item onto the stack. Then there's pop, which takes an item off of the stack. And then there is peek, which examines the contents of the topmost item in the stack. And this is useful if you want to see what's on there without actually getting rid of it. Okay, so those are the three functions that we're going to need to implement. So let's go ahead and jump over into Xcode and start working on our stack class. Okay, so this is a copy of the object-oriented linked list program that we wrote. It's the same code that was done a couple videos ago. So you'll want to go ahead and make sure that you're starting with this as a base point. Alright, so after you have that set up, we're going to add a new file, and we're going to add a new, to make our new class. So we'll right click on source, add, new file, and we have the C++ template, create a C++ file, click next. Alright, and we're going to type in stack as our new file name, make sure that we're creating a header file, and click finish. Okay, I'm going to go ahead and delete that header block. Alright, so I'm going to put my standard include guards, if not defined, stack underscore h, define stack underscore h, and if. Alright, and we know that we're going to be doing inheritance, and we know that we're going to be using the base functionality of our linked list class. So let's go ahead and import in our linked list. So #include linked list. Okay, so let's go ahead and define our class. So we do class stack :public linked list, just like we learned in the previous video. Okay, so what this has done is this is literally telling the compiler that, hey, stack is a linked list type, and I want you to pull in all of the data, or all of the member fields and all of the member functions that belong to a linked list and make them available to me. And I want to publicly expose everything that was public. Essentially what this keyword, or what this accessor level right here does is limits the scope, or it defines the highest protection level that's available. We could make this private, and which would end up hiding all of the functions in linked list, and I'll actually show you that when we get closer to completing our implementation. All right, but for now we're going to leave it as public, and we're going to create a new public section. I'm going to put my constructor, and I'm going to actually inline the implementation of our constructor. And what inlining is I'm actually just going to define the body within our header file. And I'm doing this because it's just an empty body, and we don't need to scope it over there, or scope it into our CPP file. Just less work for us in the meantime. All right, and so I'm also going to create a destructor, and we'll close that out. Okay. I'll create another public section just to break things up a little bit. And we're going to need our 3 functions. The first one is going to be push, and it's going to take an integer value to be pushed on the stack. The second one is pop, which I'm actually going to have it return the value on top of the stack. So it has a return type of int. Pop, no parameters. And the next one we are going to do is peek, and it's going to take a return an int, and it's going to be called peek. Perfect. So let's go ahead and copy in these 3 functions. Come over to our CPP file. I'll delete that header block just to clean out the code, and we will copy paste. Okay. So we need to scope in our functions. So we have stack push, stack pop, and stack peek. And we'll go ahead and create the empty bodies for each of the functions. Okay, so we know that our push function is just going to end up adding one to the end of the list. Well, the linked list implementation that we have already has a function that does that, and it's called push back. So we'll just go ahead and call that directly. Now, there is no remove in our linked list, so we have 2 options. One, we can implement that function here in pop, or we can go add it to our linked list. And I'm going to go ahead and add it to our linked list. So let's jump over here, and let's create a new function called remove back. Takes in no parameters. Okay. And then we will come over here to our CPP file, and let's implement it down here. Do void linked list, remove back. Alright, so if we jump over to our whiteboard real fast, remember our linked lists look like this. And so this remove back is going to walk down the list, find this pointer right here, or find this node right here, and delete this node. So we need to handle the case where the head pointer is null, and then we need to check to see if our list is a size of 1. Do we need to do anything special? And then what do we do for a list with multiple items in it? Okay, so let's jump over to Xcode. Okay, so if our head equals 0, go ahead and return. There's nothing to do if we don't have a head pointer. Okay, so now we're going to need a pointer, current equals head. Alright, and so while current next does not equal 0, then we need to set current equal to current next. Okay, so what that does is it walks down our entire list, so we can draw it out. So if we have our current pointer starts here, our head pointer. If the next is non-null, it updates current to now point to here. It does that until it gets all the way to here. Next is null, so current stays pointing to here. Perfect. Okay, so we have our current. Current is next. Now what we need to do is we actually need to store that previous so we can get the previous is next pointer. So when we delete this item, we still need to have a pointer to here. Actually, we don't need a pointer to here because this is always going to be null. So there's no need. Oh, no, sorry. Yeah, we need to be able to update the previous pointers next to null. I was like, what? That didn't make sense. Alright, so previous, we're going to just set that to null. Okay. And now before we update our current, we set previous equal to current. Perfect. Okay. So now if the special case is if our current pointer actually equals our head pointer. If that's the case, that means there was only one item in the list, and we need to handle the head pointer specially. So we just set head equal to 0. The head next already equals 0. And then we delete current. Okay. Otherwise, if we're not dealing with the first item in the list, then we go ahead and update the previous next pointer equals the current next pointer. Then we delete current. So the previous next is always going to be 0, so we can actually just go ahead and do that. No big deal. Alright, delete current. Okay, perfect. So now we go back over to our stack. Oh man, we actually wanted to have a return type. So that means on our header file, we need to change remove back to return an integer. Change this to return an integer. And before we actually delete these items, we need to store it. So we will create a variable called retval, and it will be current value. This way, when we delete it, we can still return the value of that pointer. Perfect. Alright, so we jump over to our stack. Our pop, now we can just call remove back. Oops. Return remove back. And that will return us back the value for the last item in the list when we remove it. Okay, so that leaves us with peek. Peek walks down the entire list and prints out or returns back the last value in the list. So there's two options. One, we can implement a function in the linked list, or we can implement it here. So for this one, I'm actually just going to go ahead and implement it here. So we have access to the node pointer because stack is a linked list. So we'll have current. We have access to head. Well, actually we don't. I'll show you the error here in a minute. But in theory, we have access to head. So we do node star current equals head. Alright, so then we do while, the same thing that we've been doing. While next does not equal null, or 0. Current equals current next, return current value. Alright, so I'm going to build this and we're going to get some other errors. We got 3 different build errors. Let's see what they are. So I changed our, let me go back over into a better view. In our linked list CPP, I changed our remove back function to return an integer now. So now we need to return some value that signifies that something kind of meaningless. So we could use -1, 1, some number that you're always going to know. And so what I'm going to use is I'm going to use the maximum negative number. Do int underbar min. And this is actually a preprocessor definition that goes ahead and defines the minimum integer based on your architecture. So a 32-bit system will have -2 to the 31st, 2 to the 31st, and then a 64-bit system will have the correct value there. So let's go ahead and build, get rid of that error, and we'll click on our next two errors. Okay, oops. So if we go over to our linked list, we're going to see we have a build error here. It says linked list node star linked list head is private. Well, that's fine and dandy. So where is it actually being used? It's being used in our stack CPP. And we can see that it is indeed here. So now the private access level means that the only person that's allowed to use the data within this scope is the class itself, so the linked list. So even though stack is deriving from a linked list, the private scope stops any inheritance chain from seeing the data below it. So what we actually want to do is we want to change this private to protected. And so the protected access level allows us to see data from our derived classes in our inheritance chain, but not expose that data to a public caller like we would use in our main CPP file when we actually start to use the stack that we created. All right, so perfect. So we'll do that. We will build. See, all is happy. So you can see that our node is also defined in the public section. I'm going to go ahead and make that part of the protected as well, because we don't really want to expose that node functionality to everybody. Okay, great. So now I'm going to jump over to our main CPP, and I'm actually going to just go ahead and delete all of this. We know that instead of you working with the linked list now, we're going to be working with our stack. Okay, so I'm just going to create a new stack variable, s. Okay, and so we'll do s push. We'll push 1, s push 2, s push 3, and then we will print out the list, or our stack, sorry. And then I will pop the value. We'll print the list here. I'll pop another one, and we'll print again, and then I'll actually push again, just so we can see how this is continually adding and removing from the end of our list. We'll print that out. All right, and then the last thing we will do is we will do our peak. So we'll just write a little message, s peak. All right. So now we've pushed 1, 2, and 3. We're going to print the stack. We'll pop it, print, pop, print the stack out again. We'll push a 4, print it, and then we'll print out our peak. So let's go ahead and build. And then we will run. And we can see that our list, or our stack, is populated with 1, 2, and 3. We popped 3, so we're left with 1 and 2. We popped 2, we're left with 1. We pushed 4 back onto the stack, or we pushed 4 onto the stack, and now our stack is 1 and 4, and our peak is 4 because 4 is the top item in our stack. Perfect. So the way that we inherited the stack class, we used the public access modifier. So that means we actually have access to all of the public functions for our linked list. So we could do push front, for example, and a value. We could build this, and this would be valid code. But we don't really want that. We implemented a stack, and we wanted to make use of the functionality of the linked list, but we don't actually want to expose additional functions. So how do we fix that? Well, it's pretty simple. We go over to our stack.h file, and we simply change our public to be protected, for example. We could use protected or private here. Protected allows someone else to come along and derive from the stack class and still have access to all the linked list items, so we'll go ahead and do that. So if I build this now, we'll get a build error. Actually get a lot of build errors. And this is because we're actually going to have to go through and clean up a bunch of different things. And so we can see that our void print, for example, is inaccessible. And that's because that protected access modifier makes that be the highest level of access that we have. So that means all of the functions are not available to anybody else. So what we need to do is we actually need to override or provide our own print functionality in our stack if we want to print things out. Okay, so let's go ahead and jump over here. We'll do void print, and I'm going to inline the function here. But the question comes up: how do we call the linked lists version of our code? And we do that by casting. So we haven't really talked about casting, but essentially it converts one type to another, or at least the compiler tries its best to do so. And so the way that we're going to do it is with a static cast, and there'll be a linked list pointer. So we're converting what this value right here, and we're saying, hey, treat this as a linked list pointer instead of whatever kind of pointer it is. And so I'm going to change this expression. I'm going to pass in the this pointer. So the this pointer is going to be pointing to an instance of our stack class, to some stack object, and it's going to be treated as a stack pointer. Well, a stack is also a linked list, so we can safely do this cast down without worrying about pointing to some piece of memory that doesn't actually act like a linked list. So I hope that makes sense. So we cast that down to a linked list. That gives us back a linked list pointer, and then we simply call the print function on it. Okay, so we rebuild. We see we went from 15 build errors to 3 build errors. That's pretty good progress. Let's see what the last 3 are. Okay, so the last one is the push front is not available. Well, we knew that. That was the whole purpose of doing this. So I'll just comment out that line and rebuild. Aha, build succeeded. Let's make sure our program still runs. So we'll clear the log. We'll run. We'll see that we got the exact same functionality from before. Perfect. There's only one other thing I want to touch on in this video. It didn't impact us in this video, but it's a very important thing to know about inheritance and virtual methods, especially since we are dynamically creating memory in our linked list class. So it's definitely possible that people that come around to derive from our classes are going to possibly be creating memory in their own versions of their code. And so that is the way that destructors work. Let me go to the whiteboard here. So there's 2 ways that we can point to our stack class that we created. Okay, this is our stack. There are 2 valid pointers that point to this. One is obviously a stack pointer. The other is the linked list pointer. And we talked about that a little bit when we did that cast. Alright, so these are both valid ways to point to this block of memory. And so, because the reason why is that we basically have this whole thing is our stack, and this is the linked list section, and here's our stack section. And when the C++ compiler works with this type right here, regardless of what kind of superclass is pointing to, the linked list is member fields member fields are always laid out in this manner, so we can always access this data safely. Okay, so we have these 2 different pointers, and so we talked about the virtual table on how functions get called during that. And so when we have a linked list, so basically whenever a type goes out of scope, it's going to use how do I want to say this? It's going to use the most solid type that the compiler has at the time. So even though that this linked list is pointing to a stack, it's going to use the destructor for a linked list, even though we're working with the stack. It's going to do that as long as the destructor is not marked as virtual. So if our stack had actually created memory, we would create memory leaks every time our stacks went out of scope because our destructors would never get called. So the way to fix that is to mark your destructors as virtual. That was a long-winded explanation just to get our virtual keyword here. But this will add our destructor to our virtual table so that when superclasses, when their objects, when their instances of the superclasses go out of scope, the correct destructor will get called. So it usually, probably 9 times out of 10, it's actually a better idea to always create your destructors with virtual so that the proper chaining can go. But like in this case, it doesn't matter because our stack doesn't create additional memory. So we're not going to end up having a memory leak. But if we wanted to come along and we wanted to create a super stack and it creates another list of items dynamically or something, when it got destructed, we would have memory leaks because our linked list wasn't marked as virtual. So in general, it's just a good idea to go ahead and mark your destructors as virtual. Okay, and so we can rebuild. You can see that actually didn't really change anything significantly for us, other than future implementations will now be more robust. Okay, so we implemented our stack here. We talked about how virtuals are working. We talked about protection levels some more. So yeah, our next video we're going to be taking a look into some of the other features that are available to us with inheritance. So look forward to seeing you then. Thanks.